Welcome to the numerical analysis course. In this lecture, we are going to study power method to compute eigenvalues of a given square matrix. In the previous lecture, we studied the method based on the characteristic equation to find the eigenvalues and eigenvectors. Right. In this method, we'll use this power method. It's an approximate iterative method. Right, and it is used to find only the significant eigenvalue. If we arrange eigenvalues in such a way that we compute only the magnitudes and we arrange them in the descending order, the largest in terms of magnitude is a significant eigenvalue. So this method finds only the significant eigenvalue and the corresponding eigenvector. Before we study the three steps that we'll use to find the eigenvalues, the iterative steps to find the significant eigenvalue of a given square matrix, we want to know some background. We know that for square matrix A, the eigenvector V is such that if we multiply A with V, the result is in the same direction as V, scaled by the corresponding eigenvalue. This vector is called eigenvector, and this lambda, the scalar value, is called eigenvalue. So if we multiply A with a vector, if we somehow know the eigenvector, and if we multiply A with that eigenvector, the result is the same eigenvector scaled by the eigenvalue lambda. So we work on this principle or this fact and keep on iterating. We'll start with a guess and keep on iterating by multiplying A with V. So we'll start with an initial guess for V, that can be any, and then we'll multiply that V with A times V, and we'll check the result. If it's in the same direction as V, we'll stop, otherwise we'll continue doing in iterations after iterations. So in order to better understand, let's start with a square matrix A, where A is given to V 1 3 2 2. It's a 2 cross 2 square matrix, and let's form step number 1, guess a value of V. You can guess any value. Let's start with 1 0. It's not an eigenvector, it's my initial guess for the eigenvector. Let's check whether it's eigenvector or not. Perform step number 2, multiply A with V. 1 3 2 2 times V 1 0, and check if the result is in the same direction as V. 1 cross 1 is 1, plus 0 is 1 2 2 0, and take the largest value common, 2. This is 1 by 2, 0.5 and 1. It's not in the same direction as 1 0, it's 0.51. It's not the same direction as V at iteration number 0. So this is step number 2's iteration 1. So we'll continue with the second iteration. We'll multiply the same A 1 3 2 2 with the new eigenvector that we have computed in the last step, 0.51. 1 times 0.5 is 0.5 plus 3, 3.5. 2 times 0.5 is 1 plus 2 is 3. Take the largest value common, 3.5. Comes out to be 1. 3 over 3.5 is 0.9 something, 0.857. Still it's not in the same direction as the V we had computed in the last iteration. So we'll have to move to the next iteration number 3. A 1 3 2 2 multiplied with a V that we had in the last iteration, 1.857. 1 times 1 is 1 plus 3 times 0.857. Let me cheat. This is 3.57 and 3.71. Take the largest value common, 3.71, and let's see, the direction is 0.96 and 1. Iteration number 4, 1 3 2 2 and the eigenvector, the vector v that we had computed in the last iteration. 1 times 0.96, 0.96 plus 3, 3.96. 2 times 0.96 plus 2 is 3.92. Take the largest value common, 3.96. The rest is 1 and 0.99. So it seems that we are converging to an eigenvector 1, 1, but we haven't yet converged to that value. So we'll keep on moving. Iteration number 5. One, 3, 2, 2 multiplied by the eigenvector we computed, the vector that we computed in the last step. 1 plus 3 times 0.99 is 3.97. 3.98. 2 times 1 plus 2 points times 0.99 is 3.98, and if you take 3.98 common, this becomes 0.991. It seems that this eigenvector, this vector is converging to 1, 1. It seems that the eigenvector is 1, 1 and the eigenvalue is around 4 that we are going to converge on. Iteration number 6. It's 1, 3, 2, 2 times the eigenvector, the vector that we computed in the last step, in the last iteration. So it becomes 3.99 and 3.99. And we take 3.99 common. This is 1, 1. And iteration number 7 is 1, 3, 2, 2, and multiplied by the vector that we computed in the last iteration is 1 plus 3 is 4, 2 times 1 plus 2 times 1, 2 plus 2 is 4. So taking 4 common, this becomes 1. This means the significant lambda, the eigenvalue is 4, and the corresponding eigenvector is 1, 1 that we have converged on. If we keep on having more iterations, iteration number 8, 9, 10, that won't change the result. The result would be the same. So we have converged to this lambda, the significant eigenvalue, and the corresponding eigenvector. That's all about the power method. We'll try to solve one more example of a 3x3 matrix in our next lecture. Right. And I have also written a Python code for this, which I will share on the WhatsApp group, and you will be able to run that Python code that I've written for this matrix, but you can try any matrix you want, and you can run that and it will show you all these iterations and the results computed in each iteration. And I'll also explain this Python code in the next lecture. Right. Thank you.